Hi, my name is Tom Adamski. I'm a specialist solution architect focusing on networking. And today I'm going to focus on global traffic management with Amazon Route 53. I'll start off with a quick introduction to what Route 53 actually is, and then I'll move on to some of the things that are very unique for the service, like the ability to scale and provide 100% availability. I'll focus on the health check, so how you validate that your service is actually up and running, and on how you can navigate traffic to your resources. I'll finish off with monitoring and how you can see what Route 53 is actually doing. So what is Route 53? It's Amazon provided DNS service. So it allows you to host both public and private domain names or zones. You can also register a domain with Route 53. You can monitor your services, your public-facing services, and navigate traffic to them using traffic management. And finally, you can use Route 53 for DNS resolution inside your private environments, inside your VPC, and configure rules and endpoints to integrate that with your on-premises data centers. The big differentiation here is between public domain names, public zones, and private domain names, private zones. Public hosted zones, which you can host on Route 53, are focusing on internet-facing resources and are usually used by clients on the internet to resolve names inside your public hosted zones. Finally, then integrate with global routing policies where you can decide how to navigate your users based on the geography or latency or other parameters. Then on the other side, we have private hosted zones. These are your private domains. They are focused on navigating traffic to resources that are inside your VPCs, inside your private environments. And typically the resolution of records inside those zones would be done from inside the VPCs as well. You can integrate those with on-premise environments using things like forwarding and Route 50 resolver endpoints. But today, we will be focusing primarily on the public hosted zones and how you can configure public zones to public-facing zones and resources pointing to your public environments on Route 53. Before we move any further, I want to do a quick summary on how Route 53 and DNS resolution generally works. So here we have a user on the left-hand side with a public IP address and a resolver that user might be using. This could be a DNS resolver inside the ISP, or it could be a corporate resolver. So a user sends a query for a particular host name, in this case www.example.com, to that local resolver. And then resolver, if it doesn't have the information in the cache, it would go through this iterative flow of trying to find out what is the IP address behind www.example.com. And the first place it would start is with the root service. So the root service already pre-configured on all of the resolvers, so they know how to get to the root service. And they would forward the query for the whole host name to the root service. However, the root service don't actually have any knowledge about the specific information inside www.example.com. But what they do know is who is responsible for the top-level domain for the host name, from the host name in the query. And in that case, the top-level domain is .com. So those name servers are returned to our resolver, and the resolver forwards the query to the top-level servers. Again, in this case, the top-level servers don't have all the details about what records are under www, but what they do know is who is responsible for example.com. And if you are using Route 53 for hosting your public zone, that would be the Route 53 service. And in that case, the resolver forwards the query for www.example.com, and Route 53, because it's authoritative for the domain, it can respond with a specific answer for what's the record, what's the IP address behind the www, and that gets returned to the user. One thing to call out here is that the Route 53 service can make an intelligent decision on what to return to, what answer to return to the query based on the geography or some additional information about the resolver, or if the resolver supports DNS extensions of client subnet, the resolver can pass on the client subnet of the actual client for Route 53 to be able to do a more specific decision. But we'll dive into those options in a second when we will talk about the routing. First, I want to start talking about the scale and availability. So DNS is critical to the availability of your application. So no matter how you scale your application, how highly available it is, if the DNS is not working, your clients will not be able to consume your service, your clients will not be able to connect to your application. So Route 53 provides 100% availability SLA, which means that we work towards allowing every query to have an answer. Make sure that every query that you send to Route 53 gets responded every time. And if you follow the QR code, that's actually the 100% availability SLA. You can read through that. But I want to spend some time on explaining how are we architecting the platform to actually be able to achieve that level of availability. So when you create your public hosted zones on AWS and you decide to host it in Route 53, we will allocate 4 name servers to be responsible for your zone. In the example here, you can see the public zone called example.com, and there are 4 name servers that are authoritative for this domain. These are Route 53 assigned name servers. And if you zoom in closer on the top-level domains, you will find out that they're from 4 different top-level domains. We have the .com, we have .net, we have .co.uk, and we have .org. So what does it mean? So these 4 different domains are actually separate from a management and from the data plane point of view. So on the AWS side, we call them stripes, and they're independent from each other, which allows us to add an extra level of availability. So if we're making changes, if there's issues with the data plane, that would typically affect a single stripe, not 4 stripes at the same time. And within each one of those stripes, we have thousands of unique name servers, each one with its own IP address. And so we have name servers for .com, we have name servers for .net, we have name servers for .co.uk and .org. And when you decide to host a domain on Route 53, let's say example.com, 4 of those name servers would be allocated to become authoritative for your domain. If you then, or another customer creates a separate hosted zone, a separate domain, let's say amazondomains.com, another set of 4 name servers would be allocated to be authoritative for that domain. And if you notice here, we have 1 server overlapping, 3 servers are unique. The mechanism we use to allocate name servers is called shuffle sharding, and it ensures that we don't have a case where more than 2 name servers are overlapping. So the maximum overlap with name servers for 2 separate zones would be 2 name servers. And that gives us, again, an extra level of availability, which means you're not affected by any noisy neighbor problems when one of the domains has a lot of traffic versus the other. If you want to learn more about shuffle sharding and how that mechanism works, there's a really good blog post by one of the principal engineers, and you can follow the QR code to read a little bit more about that. But how does the shuffle sharding and the server allocation translate into physical infrastructure, into the physical deployment? So if we look at the AWS global infrastructure, you have 24 regions deployed across the world with 77 availability zones. We've announced already a list of additional regions that we're planning to launch, and it's growing. But today we won't be focusing on the regions. Today we are focusing on the Route 53 locations, Route 53 POPs, which we have over 150 around the world. If you follow the QR code, you'll see the different geographical locations where these points of presence are deployed. And this is where we host those different name servers that are authoritative for the public hosted zones. So if we make this a little bit simpler, and we just focus on a small subset of those Route 53 POPs. And if we zoom in on just one of the name servers, from the .org stripe, so you'll notice that same name server is actually deployed across different locations around the world. And it also has a unique IP address, but it's using the same IP address in all of those locations and being advertised as the same Anycast IP address from all those locations around the world, which means that if a name server, if a resolver tries to query our example domain and it gets directed to .org, depending on where the resolver is, it will be directed to the closest Route 53 POP where that server is hosted. So if I'm in South America, I'll get to the POP in South America. If I'm in Europe, I'm going to go to the POP in Europe, which means I'm getting to the closest server that's available to me. But that's just a single stripe. That's just the .org stripe. And we do the similar thing for all the other stripes. So .com, .net, .co.uk also spread around the world. Typically, a single server from a particular stripe would have its own POP, its own location. In some bigger areas, there might be cases like in the drawing where we would have up to 2 servers sharing the same POP. So what's the benefit? Why do we do it? Again, this is all about availability. So if we look at a very simple example here with 3 POPs, and for simplicity's sake, let's say the first one actually is hosting two of the authoritative name servers, .com and .org. The other one is just hosting .net, and the last one is hosting .org and .co.uk. If we have a name server that's trying to resolve example.com and gets directed to those locations, it would pick the one that's usually responding the fastest. So maybe it's the top left corner, maybe it's the .com IP address ending with .10 that's responding the fastest. That's the one that resolvers end up using for querying example.com. Now, if there's a failure of the whole POP, the resolver can easily reroute the traffic to another location. So even if it was the .org, we actually have another location advertising .org. If it's .com and that was the closest .com, we can probably find another .com in another location. It can also survive a more complex failure. So imagine there's an issue with the network provider, the transit provider where your resolver lives or where your network is. And some of the traffic is getting incorrectly blackholed by the transit provider. Because we don't advertise all 4 name servers from the same location, even if some of the traffic is blackholed, the resolver still has the ability to try all the other locations. It still has ability to get an answer for the query. So that, combined with the shuffle sharding, with the Anycast IP address, gives us the ability to offer that 100% SLA to make sure that when you are sending a query to Route 53, you always get an answer. I also want to touch here on another quite different use case of Route 53 in China. So China is managed as a separate network, independent from the global AWS network. And even when you configure services in China, you would use a separate console. So that applies also to Route 53. So Route 53 has an independent deployment in China, and there's a separate deployment in Route 53 Global. And with China, we actually have 4 locations in China and 2 locations outside of China that are hosting those different name servers. In this scenario, we still do shuffle sharding, so we still make sure that no more than 2 servers overlap between zones, but we don't do Anycast. Because we have 6 locations, each location would have its own unique IP address. And when you create your zones, the recommendation is to have a different domain, different zone for Route 53 Global, and different domain for Route 53 China. So in this case, example.com would be in global, example.cn would be in China. And if you want to see how that China domain would look like, you can see here that instead of the 4 name servers that we see with Route 53 Global, we would see 6 name servers, each one in one of those 6 locations that I showed you earlier. So for some of the best practices with Route 53 China, As mentioned before, make sure you treat them as independent environment, so it makes sense to have a completely separate domain in Route 53 Global and separate domain in Route 53 China. If you don't want to use the same domain, you decided you want example.com to be accessible both in China as well as in Route 53 Global, you can configure a subdomain, for example, cn.example.com, and delegate that to the China environment. Just make sure you set up your TTLs very high so that the queries don't have to traverse the Chinese border. There is some performance penalty applied there. Finally, always review the functionality differences between what's available in global environment versus what's available in China. And if you want to read more about best practices for deploying Route 53 in China as well as CloudFront, in China, you can follow this QR code. My colleagues Christian and Rizwan have written a really good blog post that goes into the details. Okay, so we understand the availability now. Let's dive into how you can validate your resources that are up and running, and then how you can intelligently route traffic to them. So let's start with the health checks. So health checks allow you to validate if your public-facing resource, or sometimes internal resource, is up and running. Depends on which health checks you're going to use. So we support 3 different types of health checks. Just health checking a particular resource, a combination of multiple health checks, and then finally a health check that is based on an Amazon CloudWatch alarm. And CloudWatch is a monitoring service that can generate alarms when things go wrong, and you can use that as to feed the Route 53 health checks. So let's start with the first one. So just health checking an endpoint. So this is only supported for public-facing endpoints. So your resources have to be facing the internet, have a public IP address that can be tested. And then we have 8 different health checker regions that would be sending checks to your public-facing resource to make sure it's up and running. If at least 18%, 18%, deem the resources up and running, we assume that it's up and running. When you do configure the health check, you can specify what methodology you want to use to test your resource, whether it's HTTP, HTTPS, or TCP. You can specify an IP address or a domain to test, the port, the index. You can decide how often do you want to test, how many failures do you want to see before you consider a health check unhealthy. You also have the option to do string matching and customization to which one of the health checker regions you want to use out of the 8 that are supported. And then you can also enable latency graphs. So if you want to start measuring how long it takes to connect to your service from all the different regions, you can start capturing that in graphs and then visualize it in CloudWatch. Another option for health checking is to create an aggregate health checks, consolidated from multiple different health checks. So in this example here, we have 3 different health checks. 2 are healthy, 1 is unhealthy, and we've set the threshold to 2. So it means at least 2 have to be healthy for the consolidated health check to be healthy, and 2 are healthy, so we're fine, this is healthy. This is very useful if you're thinking about disaster scenarios where you want to fail over the whole region or one big environment if there are enough failures of the smaller components. Finally, the last health check option is the one that's based on CloudWatch alarms. So there are some default CloudWatch alarms. For example, for an instance, we would be monitoring the status of an instance, and if that instance fails, there would be a status failed check alarm kicked off. And if that alarm is alarming, you would treat the Route 53 health check as unhealthy, and if there's no alarm, that resource would be treated as healthy. And I've got another blog post here for you if you follow the QR code. That goes into the details of creating really custom ways to test even your internal resources and then push the information into CloudWatch alarms and then use that for Route 53 health checks. Okay, so now we know if our resource is healthy or unhealthy, and let's look how we can use that intelligently in the routing mechanisms. So AWS Route 53, Amazon Route 53 supports 7 different routing mechanisms. 6 are available easily in the console. The 7th one is available for a different part of the console. That's why it's drawn separately here, but there's 7 in total, and we'll go into each one separately. So in the examples, we'll have the resolver on the left-hand side. We'll have our Route 53 configuration on the right-hand side. And I'm using IP addresses as the resources that we want to route traffic to. But Route 53 supports all sorts of different types of targets. It could be a CNAME. It could be an alias record that points to a specific AWS resource. But for simplicity, I'm just using IP addresses so it's easier to visualize. So in the simple example of setting up a simple record, we're just doing a mapping between a name and a single or multiple IP addresses. So if a resolver sends a query for that name, Route 53 will respond with the appropriate information mapped to that name. If we want to go more advanced, we can set up failover routing. In this scenario, we're setting up the same name twice, but as primary and secondary. And we associate a health check with our resources. So as long as our resources are healthy, the query going to Route 53 will return the primary resource. If that primary resource becomes unhealthy, the query for that resource will return the secondary. Moving more towards more advanced deployments where you want to return multiple resources but maybe have a health check associated with each one. You can absolutely do that with multi-value answer. In this scenario, you create multiple records with the same name, pointing to unique resources with each one with an individual health check. So if all of the health checks are healthy and the query comes from for that name, multi.example.com, Route 53 would return all 4 resources to the resolver, and then the client can decide which one to connect to. It's a simple way to add a certain level of load balancing. And multi-value answers support up to 8 different answers that can be returned. Even if you have more resources, even if you have 10, 20 resources configured, we would always return up to 8 at a randomized way. So each one has a health check. So it's one of our resources goes unhealthy and another query comes for the same name, only the resources that are healthy would be returned. Continuing on the load balancing side, you can also configure weights to apply decisions of how often do you want to return a particular name to the resolver. So here we've configured weights of 50, 30, 20, easily adding up to 100. So it means the first one will be returned around 50% of the time, the second 30% of the time, last one 20% of the time. So resolver sends a query for the weighted record, for the weighted name, weight.example.com, and it's quite likely that it's the first one that will be returned. And if there's any issues, if there's health check failures, that record would be removed from circulation. So only the first one and the third one would be returned for all the queries. Now, if we want to make a routing decision based on the location of our clients or where the resolver is, we can do that with geolocation routing. We can configure it so that depending on which country, which continent, or which state in US the traffic is coming from, we can return a different IP address, different answer. So in this example, we have 3 different geographies. We have the default, which is like a catch-all. We have North America and Europe. So if we have a query coming in from North America for our geolocationexample.com, we would look at our configuration and return the record mapped to that geography. If it comes from Europe, we do exactly the same thing. If it comes from anywhere else outside of the regions we defined, or if we can't actually find out exactly where the IP address belongs to, it would fall under the default answer and we would respond with the default record. If you're more interested in making the decision based on performance, you can configure latency-based routing. In that scenario, we're doing latency measurements for internet paths to AWS regions. So we would have a database of IP addresses and we would know how long it would take, what's the latency from each one of those IP address ranges to go over the internet to reach AWS regions. And in our example, we have Oregon, we have Virginia, and we have Sydney. And if we look at the latency measurements, our resolver is in London, so maybe over the internet it takes around 270 milliseconds to get to Sydney, 80 milliseconds to North Virginia, and then 140 milliseconds to Oregon. So in that scenario, the IP address we want to return is the one in North Virginia because that's the region that's closest to our resolver, to our client, from a latency point of view. Finally, another performance-focused routing mechanism is geoproximity. In this scenario, we're focusing more on the geographical location of the clients and geographical location of AWS regions or your own physical data centers. So we still have 3 AWS regions, but we've now added a Moscow on-premise data center. And we want to make a decision, again, based on the geography and proximity from the resolver and the client to the resources they're trying to access. And when you configure geoproximity, you actually get a visualization. You get this map that you see in the bottom right corner that defines which clients would be sent to which region. So if I'm in South America, I would be sent to North Virginia. If I'm in Australia, I would go to Sydney. Our resolver is in London. So if we receive the query from a London-based resolver or London-based client, we see that it falls under area 4. So in that case, we would return the IP address representing a Moscow data center. And you have the option to adjust biases on the size of each area. So maybe you think that the Moscow data center is covering too much of an area, you can adjust that and give more area to other environments. So summarizing the policies, if you want to failover between resources, use the failover policy and health checks, and actually use health checks everywhere. If you want to load balance across different environments, think about weighted policy or multi-value answer. If you want to select targets based on performance, that's latency-based routing or geoproximity. And finally, if you are just making decision based on the country or continent of the resolver, that's where you use geolocation. Now, if you want to use all of these policies, you can. So we give you the option in the traffic policy to create layers of your routing policies that can intelligently define what answers are you returning for a particular query. And again, you get a visualization, so you can build it in the console. You can also use APIs. And in this simple example, we're actually combining 2 of the routing policies. We're combining weighted and we're combining multi-value answer. So if the weighted policy gets triggered first and we hit the top weight of 10, then based on that, we would return, instead of a single answer, we can then return multi-value answer with 2 records. And we would obviously associate health checks to make sure these resources are up and running for us. Okay, so I want to finish off with highlighting some of the monitoring options. So how do you know Route 53 is working? What data can you get out of it? You can use CloudWatch to see the DNS query metrics, to see actually how many queries each one of your domains, each one of your zones is getting. And then if you want, you can set up thresholds or even set up anomaly detection. So this is part of CloudWatch, where you can enable anomaly detection that would apply machine learning algorithms to understand your patterns and then alert you if the number of queries is outside of the usual pattern. There's an anomaly. This could be very useful to see that, maybe one day you're not getting enough queries to your domain, and that means that something might be wrong. Same if you're getting too many queries. Finally, we also support logging. So you can enable logging for all of your queries on the public hosted zones to start seeing things like what the query was for, what was the time of it, the record type, and so on. Here are some examples that show you what the logs would look like. So first, in white, the 10, it's the version. Then we see the date and timestamp. Then we see the ID of the zone beginning with Z. And then we actually have the query. So example.com, badexample.com. We see also what the query was for. Was it an A record? Was it a quad A record? Was it successful? So error or not existing domain. What protocol was used? UDP, TCP. And then finally, you can see the little FRA6, IID12. These are airport codes representing the Route 53 locations that were responding to your queries. And finally, in white, you see the IP address of the resolver. So this is what we would make the routing decision on if we're doing geo-routing, latency-based routing. And then if the resolver supports client subnet extension, it would also give us the subnet belonging to the actual client, so we can be more granular about our routing decision. That's what you see in 3 of the logs here at the very end. All right, thank you very much for your time. I hope that was useful. Please complete the session survey. Let us know your feedback. We do look at it. We do update our content based on the feedback from you guys. Thank you.